Let's look at OpenStax University Physics, Chapter 16, Problem 110. A string with a linear mass density of 0.0075 kilograms per meter and a length of 6 meters is set into the n equals 4 mode of resonance by driving with a frequency of 100 hertz. What is the tension in the string? So here I have a diagram. This is the string. It's constrained at both ends, and we get 4 different patterns for n equals 4. And then I pulled some useful equations that we're going to be using. So this equation, F sub n is nv over 2L, is for the nth frequency for a string that vibrates when it is constrained at both ends. And then v is square root of force divided by m over L, or by the linear density of the string, is the speed of a wave on a string. So let's write down the things that we know. The linear mass density, so that is m over L, is 0.0075 kilograms per meter. And we know that the length is 6 meters. So this is 6 meters. We know that n is 4. And the frequency corresponding to that n is 100.00 hertz. We're looking for the tension in the string. I'm going to call it F sub t so that we don't confuse it with period. So we know from the two equations, so I'll rewrite them. F sub n is nv over 2L. In our case, n is 4, so F sub 4 is 4v divided by 2L. And then we also know that v is square root of the tension force divided by m over L. So I can solve for the velocity in the first equation, and that gives me v is 2L F sub 4 divided by 4. And I can set this equal to that. So then 2L F sub 4 divided by 4 is equal to square root the tension force divided by m over L. If I square both sides and solve for the tension force, then I have 2L F4 divided by 4 quantity squared times m over L. So the tension force will be 2 times length is 6 meters. Frequency is 100.00 hertz. Divide this by 4 quantity squared. And the linear density of the string is 0.0075 kilograms per meter. And when we multiply these numbers together, we end up with 675 newtons. So the tension in the string is 675 newtons.